Okay, welcome everyone. Sorry for the change of venue. Um, get everyone marked in here. All right. Yeah, so I was not feeling great for some of this weekend. I'm getting tested today to see if I'm going to be missing for longer. I am feeling better though, so hopefully it was just a one-day thing. As I mentioned in the announcement last night, because I'm not on campus today, that does mean that lab is going to be remote today. And I'll keep everyone updated on when we might get back into the classroom. So today, what we're really going to be focusing on is the big kind of integration gun from Calculus 1, which is U-substitution. And so we saw, again, very preliminary example of that last class, but a lot of today will be, besides just getting some more examples, also seeing a little bit of the nuance. How flexible is this method? What are the different situations in which we can use it? So as a first example, so we have the integral of x e to the x squared dx. So looking at this, what you'll want to develop, especially as we get into the techniques of integration part of the course, you'll want to look at this and think, what means of integrating things do I have, and which of those best applies to this? And really, before we start seeing new things, what we have is it something that we can just use an integral rule, like the reverse of a derivative rule, and no, this is too complicated for that. Another thing is, can we do any algebra to make it simpler? And in this case, there's no simplifying to be done. And at least what I tell my Calc 1 students, if those, at least in Calc 1, if you can't do either of those, you're really stuck with U-substitution. But from a more kind of sophisticated point of view, what you can really do is say, looking at this, there's an inside function, this x squared, inside, meaning also up in the exponent, and then there's this outside function x, and the derivative of x squared is basically x. So looking at that kind of feature of this integral really suggests this is a good U-substitution integral. So we go ahead and try to do the U-substitution. So U is the inside function, so that's x squared. Take the derivative, du is 2x dx. And then what we see is that back to the u is x squared. That handles what's up in the exponent. But then the issue is that we have this du equals 2x dx, and the x stuff that we have is just x dx. So a problem can be that you might be off by a constant. But if you're ever off by a multiplicative constant, that's always fine. You can always say, I have x dx, I don't literally have that on the right side of this substitution equation here, but I can get literally x dx by moving this 2 around, because this is an equation and we have algebra that says we can move stuff around. So dividing by 2 or multiplying by a half, we get 1/2 du is x dx. And now we actually have what shows up in our integral. So then we can say e to the x squared becomes e to the u, making that substitution. X dx gets replaced with this 1/2 du. And once we have it written like this, we're able to integrate it. The half comes along, e to the u stays e to the u. And then once we've actually done the integration, substitute back. We started with x's, let's end with x's. So we get 1/2 e to the x squared plus c. Questions about this problem? Hopefully this is familiar, but if any part of it you're a little unsure of, making you more sure of it is really important before we get into some new stuff. Okay. So this sort of moving constants around is really something that you'll have to do fairly often, and you'll want to know that you're always able to do it. This move can also help with some integrals where you don't necessarily need to think of it in terms of U-substitution. So for instance, what if I had this sine of 1/3 x dx? So one way that you can view this problem, and that we've seen some examples that are really close to it, because we have this extra constant, how we can do this is integrate this function. So that's negative cosine. We leave the inside alone, and then we divide by that new, by the function that, sorry, not the function, the constant that's inside. And dividing by 1/3 gives you 3. And so we can simplify that. But what you can also do, and this is something that if you just like the formalism of U-substitution, you can also do. So what you can say is we have an inside function here. So let's say that u is 1/3 x. Take the derivative, du is 1/3 dx. And now if you're trying to pair things up to do this translation, the 1/3 x, that's going to become a u. This second equation, we have the dx, we don't have the 1/3, but as we know, if you're just off by a constant, you can always move that around to make it match. So multiplying both sides by 3, we get 3 du equals dx, and now we have just dx, which is the other thing that shows up in our integral. So making these replacements, dx becomes 3 du, and sine of 1/3 x becomes sine of u. Once we're here, we can integrate. Sine becomes negative cosine. And then we can replace u by what it was originally, 1/3 x. We can also move this 3 in front. -3 cosine of 1/3 x. So if you like to think of this kind of problem as if there's an extra constant, I have to divide by that constant, but can otherwise just integrate normally. You can also think of it as a U-substitution where basically the only thing you're doing is moving this constant around. Either one of these is fine. And if you like this longer but sort of more systematic way of doing U-substitution, then use it. So let's try another example here. Let's do the integral of x squared over 1 plus x cubed dx. Okay. So when U-substitution is described, a big way that it's done is, or the kind of way the guiding principle is stated, is that U is the inside function, or you take the inside function and make that your U. And the way that that's phrased can be a little deceptive. It's the word inside, I mean. For instance, going back a case, inside in this case means up in the exponent, which isn't typically what you think of inside, but still counts. It's inside that exponential function. Another way of what inside can mean is in the denominator. So in this case, we can't just integrate it straight away. There's no algebra to do. We can't break this up because that's not how these fractions work. And so we'll need to do U substitution. And so our choice of U is going to be what's in the bottom. That works because the derivative is basically x squared, so that's good. And in fact, if we want to kind of separate this, and this is a step that you don't ever have to do, but sometimes breaking things apart can kind of make it clearer what the different pieces are. But another reason why the bottom is a good choice for you is that you never want to be in a situation where you would try to put some kind of du in the denominator. If we're thinking of this as a fraction, the dx is always on the top. So the du is also, whenever you do the substitution, is also going to be on the top. So that means whatever is happening on the bottom really has to be subsumed by this choice of what u is going to be. So if we make this choice, u is 1 plus x cubed, then we take our derivative. The 1 goes away. The power rule gives us 3x squared dx. We're off by a constant, but that kind of being off is something we can always overcome. So divide both sides by 3. 1/3 du is x squared dx. And now we can make the substitution. So I'll keep color coding everything. 1 plus x cubed, that's getting replaced by u. And this x squared dx, now we have that literally in this equation, that's going to become 1/3 du. So 1 over u times 1/3 du. The 1/3 is going to be there, so we can write that. 1 over u, I don't think that's shown up in any of our examples yet, but this becomes the natural log, or or specifically the natural log of the absolute value of u. The absolute value is because if you check it as a piecewise function, it works, but also the natural log allows this to make sense for negative inputs. And 1 over u makes sense for everything other than 0, so we don't want to lose half the function. And then as our last step, we'll put our function 1 plus x cubed back in for u. Questions about this problem? Either kind of generally how U-substitution works, or if there's a kind of specific step that you're wondering about, or just a place where you become less sure of how it's all working.
When you said 1 over u becomes natural log, is that specifically because it's u, or is that because of what u stands for?
So this is so it's not really the, wait, so you're saying this step?
Yes.
So that is one of the integral rules. So I think the u is just sort of the letter we're using. The integral rule you typically see would be something like 1 over x become, the integral of 1 over x is the natural log of the absolute value of x plus c. So that, I think x is just the usual letter that gets used. So this is typically what, I think in the textbook, this is how it would be written. And if you change the letter, that doesn't affect anything.
Okay.
Yeah, it's kind of the dual version of the derivative of the natural log is 1 over x, and we reverse that. Okay. Any other questions? Okay. So to give everyone a little chance to try this out, I'm gonna, I don't want to be blue anymore. Oh, sure. I'm going to pause for a little bit and give you a chance to try a problem out like this. So let's try the integral of e to the x over 1 plus e to the x squared dx. So this is a U-substitution problem. Try to work it out. I'll just give you a few minutes. If you don't finish, no worries, we'll go over it. But just as a chance to check how well you're, I guess, understanding U-substitution or remembering U-substitution, I want to give you a shot for this. So I'm going to be quiet for a few minutes. If you have any questions, drop them in the chat and I'll respond, but we'll come back in a little bit to talk about this. Okay, so that's not very long, but hopefully at least everyone got a chance to look at this and think about if we're going to use U substitution, what is the U? That's really, so it's the first real step, but also getting proficient at choosing the correct U to start with is really important because if you make the wrong choice of U, then the process just isn't going to work. And I should also say right there, if you're trying U substitution and it seems like it's not working, but you're pretty sure U substitution is the method you want to use, maybe go back and say, did I choose the right U, or is there a different option that I could have taken? So putting this example back up, what is the U that some people chose to start their U substitution? Okay, 1 plus c to the x, right. So in this case, I think one thing that is worth bringing up is why wouldn't you choose just the entire bottom? Going back an example, I picked 1 plus x cubed as the, let's actually go back here. In the previous example, I chose 1 plus x cubed here and the whole bottom, and it worked out here. In this case, if you tried the entire denominator, what would happen would be if you choose that to be u, you take the derivative to get du. The derivative of this at least is going to be a chain rule problem and is a lot of stuff which isn't really available. We can't find the way to substitute, or we can't find where we would substitute it in the equation here. So while I won't do it, what could be a valuable exercise is see what happens if you choose u to be the entire bottom and see what just doesn't work. But on the other hand, if we say u is 1 plus e to the x, then the derivative, the 1 goes away, we get e to the x dx, and that is what shows up right there. And our u is what's inside our square. And then what is still here to code everything, this 2 is just going to be here. Sometimes, or if there's we have the inside thing that is u, the thing that is outside just sticks around. So if we make this substitution, and now because du equals e to the x dx, that matches exactly with what is in our integral. We don't have to move any constants around. We can just go for it. So rewriting this, I'll say 1 over 1 plus e to the x is u, so that's u squared, and then e to the x dx becomes this du. From here, it's a mostly straightforward integral problem, but is everyone on board getting to this point? Okay. So once we're here, a step that you might want to do, but potentially don't have to, is to see what this integral is. It can make things easier to rewrite this with a negative exponent. Writing it with as an u to the negative 2 makes it clear how the power rule is what you really want to do here. And so that means we increase the exponent by 1. Going up, we get less negative, and then divide by our new exponent. We can move a bunch of things around with these negatives. U to the negative 1 means in the denominator, this is a negative sign that can really go wherever we want in the fraction, so we'll put that on top. And then the last thing would be replace u with the function that it was in terms of x. So negative 1 over 1 plus e to the x plus c. Questions about any steps of this, or sort of more general U substitution questions? Okay. So with U substitution, getting into some of the more flexible ways that it can be used, with this problem, the integral of tangent, this is a U substitution problem. And hearing that, you can look at this and say, how? How could this be a U substitution problem when there's only one piece here? There's not an inside or an outside. There's just this single function tangent. And the way that we can make it happen is doing a little algebra to make there be more than one thing here. So tangent is sine over cosine dx. And now we can see there's more than one thing here. And so if this is going to be a U substitution problem, what is U going to be? Sounds like a horribly ungrammatical sentence. So there are really two options, sine or cosine. What's the better choice for you? And feel free to unmute and chime in if you know what it should be.
Cosine.
Why? Yes, I should say that first. Yes, but why? Why is that the better choice for you?
Is that because the derivative of sine is cos?
So I think right there, the derivative of sine is cosine is really sort of a misleading fact. That would say that if that could mean that sine is also a valid choice because its derivative is also in this integral. But it turns out that isn't the choice you want to make. So cosine is the choice. And its derivative is negative sine, which is also up to a minus sign here. But why would we prefer cosine over sine?
Is it because its antiderivative is sine?
So I think that's sort of what another way of what I just mentioned a little bit, that these guys have they're related. You can get from one to the other by taking some derivatives. I think the big reason that I was that I think of, right. So in the chat, Garrett mentioned, it's in the denominator. So I think if you go back a few examples, I had said, you never want to make a choice that forces you to try to put du in the denominator or pair your du equation with whatever's in the bottom. Because this dx, if we think of this as a fraction, is in the top part. And so when we switch from dx to du, that also needs to be in the top part. So in this case, what is, I think why this is worth stopping and talking about a little bit, is that it can be misleading because it seems like no matter which one of these you pick, sine or cosine, the derivative is also around, which is a big thing that has to happen if you're going to do U-substitution. But why cosine's the right choice, and we'll execute this here, is that du is negative sine x dx. And if we break this apart, sort of rewriting it into the pieces that we're going to be doing some substituting with, we have 1 over cosine, and then we have sine x dx. And so now this is set up, except for this minus sign, to actually do these substitutions. Maybe as a the thing that wouldn't work is if you said u is sine x, du is cosine x dx. But what would happen in the integral, if you tried to separate it like this, you would get sine x and then dx over cosine x. If we try to do this separation like I did here. And here it just doesn't end up working. We're treating this dx like it's in the top. And so we can't pair it with something that's in the bottom. I feel like bad is a little strong, isn't going to work the way we want it to. Okay. And actually, I should say, if you made this choice, which at first, just the part of it where the derivative of sine is also around, that's a reasonable choice to make. But then when you get the substitution step, you'll see, oh, this isn't going to work. Then you can stop and say, I feel like U-substitution should work, but this isn't going to get me to the end. Maybe you need to go back and revisit what my U was. Right. So the way that's going to end up working with U as cosine, we can move this minus sign around because we don't have it actually in the integral. And then we can substitute in. So 1 over cosine becomes 1 over U. Sine x, now we have that actually appearing in one of these equations, becomes negative du, or rewriting it in a more kind of normal looking way, negative 1 over u. And now we can integrate this. As we saw in a previous example, this isn't a power rule problem, even though it is u to the negative 1. This is a natural log integral. And then we can replace u with what it was when we did the substitution cosine. And that's the integral of tangent. Questions about any part of this problem? Anything that I said that wasn't really clear, or any step that you'd like me to explain where it, how we actually make that move? As one very last thing about this, which is mostly just in case you see it somewhere, I don't want you to be too surprised. Sometimes this integral rule is phrased a different way. So if you remember, there are these logarithm rules, one of which says you can move exponents in front of logarithms. So in this case, if we reverse that and say we have cosine to the -1, so instead of this negative in front, moving it up as an exponent, cosine to the -1, not an inverse, but reciprocal. So this is the natural log of secant plus c. So either one of these is fine. It really doesn't matter. They're equal. Just using a log rule to get from one to the other. But sometimes this shows up, and don't be alarmed if you see it and think that's not what we saw in class. Just it's a little simplification that sometimes people do. So one thing that we should bring up that we actually haven't yet is, how do you deal with definite integrals that need U-substitution? So everything we've been doing has been indefinite integrals. What happens if you have bounds? So let's integrate from e to e to the 4th over 1/x natural log of x squared. So this is going to be some number corresponding to the signed area. But the way that we actually do this is, well, there are two ways. Either one works. It comes down to what you like. The first way is find the indefinite integral first. Meaning, forget about the bounds, just do U-substitution in the way we've been doing it. And then once you know that antiderivative, go back and use that fact in the fundamental theorem of calculus. So second, which is a little unclear exactly what I mean, but we'll see what that example looks like, is that we can also translate the bounds from x to u. Okay. I'll explain what that is when we get to that second method. So for way one, what I mean is, we'll worry about the bounds later. Let's just actually do the U-substitution. And in here, if we're doing U-substitution, we really need to decide, well, is this the right kind of integral for U-substitution, and what's the U going to be? The way to break this apart that can help is, we have 1 over the natural log of x squared, and then 1 over x dx. This separation helps us see a little more clearly that u can be the natural log of x and the derivative of the natural log is 1 over x. Where when it's all one fraction, it's harder to see. I think it's in particular, seeing that there's a 1 over x function there really helps clarify that we have a couple different functions and that we want u to be the natural log, and so its derivative is 1 over x dx. So if we make that choice, then our integral 1 over x dx all gets sucked into du. The natural log becomes u. This is a power rule problem. Skipping to what it ends up being, this is 1 over, or negative 1 over u plus c, and then u was the natural log of x. Questions about this u substitution? So this is not really what we want to do, but it's a big part of it. So if we go back to the problem that we were given, integral from e to the fourth, 1 over x natural log of x squared. The fundamental theorem of calculus says, if you want to know this definite integral, step 1, find an antiderivative. Step 2, plug in these endpoints and subtract. And what this first part is this is finding that antiderivative for us. So we can just look at the end here and not worry about the c because that's just not important for definite integrals. This is an antiderivative. We had to work to find it, but we did end up finding it. So what we can say is take that antiderivative and evaluate it from e to the fourth. And now this is some number that we can compute. So first we put in e to the fourth and then subtract what we get when we put in e. Okay. And this actually works out really nicely. You could go to your calculator, which would work, but in this case, what happens is the natural log and e cancel, giving us just the exponent. So in this first case, the natural log of e to the fourth is just that 4 in the exponent. These negatives cancel, and the natural log of e is 1. Okay. So this is one way that we can handle definite integrals. Just do the u substitution totally separately. Once you get that function, that's the thing that shows up when you're using the fundamental theorem. Okay. But what about this other way? So let's put this function back here, e to the fourth. 1 over x natural log of x squared dx. Okay. So in this case, it's exactly the same u substitution. So u is going to be the natural log of x, du is going to be 1 over x dx, and we see those pieces there. So this will be sort of incomplete, but when we do this u substitution, we end up like we did before with 1 over u squared du. But what we can't do is just use those same bounds. So red for warning, because this definite integral is some kind of area. And if you change the function, you're going to change the area too. So the question is, what bounds do we have to put here so when we integrate this function over that new interval, we get the same area as integrating the old function over the old interval? Which is kind of a weird thing to ask, but there's actually a systematic way of coming up with what those new numbers are. We can actually use this same equation here, u is the natural log of x. Because we can say, okay, x equals e. Nope, this is going to be good this time. So what we can say is this lower bound e, put that e into the natural log and see what the corresponding u is. And we get 1 out. And then do the same thing with the top. X equals e to the 4th, put that into this first equation, the natural log of e to the 4th, and we get 4. And these are our new bounds. So what this is saying is if you have this original function over this original interval, if you change the function by doing this substitution, by u as the natural log of x, to make sure you get the same area, instead of integrating from e to the 4th, you have to integrate from 1 to 4. And how you come up with those numbers is you use the same thing that changed the function to change the numbers. Questions or parts of that you would just like me to kind of try to walk through again? Because it's sort of a weird thing to do. All right, so in summary, if you want the same area from the definite integral, if you change the function, you have to use that same equation to change the numbers. But once you're here, you can say, well, this is a definite integral, let's do it. And so 1 over u squared, that's something we know how to integrate. Putting in these numbers, we get -1/4 minus -1 over 1. That's -1/4 plus 1, which is 3/4, which is the same number that we got before. And actually, if you look at especially this last part, -1/4 minus -1, that was exactly what we got here. Just the thing was that this had the unsimplified version, natural log of e and natural log of e to the 4th. Where here, we already did that substitution. We found the natural log of e and the natural log of e to the 4th, and we just used those outputs as our numbers here. So these two methods give us the same answer. It's just, is there one that kind of makes more sense to you? If you don't really like this move of changing the bounds, don't worry about it and just do the indefinite version first. Okay. So where we're gonna be next time There's a different use of U-substitution that I want to talk about, which kind of indicates the direction we might go with these techniques of integration, more flexible, different uses of, or different ways of integrating. So watch your email. I'll let everyone know kind of what the updates are as far as being remote or not. This video is going to get posted on the Canvas page. So if you want to watch some of it again, or some parts of it you didn't get to write down if you were taking notes, that'll be up there. And I'll see all of you Wednesday or remotely for lab today, if you have that.